Welcome all. In this lecture, we will be discussing about some more properties of Fourier transform. Next property is differentiation of in time. So suppose x of j omega is the Fourier transform of x of t, then f of differential of x of t is equal to j omega into x of j omega. So let us consider proof of this property. So we have the inverse Fourier transform as x of t is equal to 1 by 2 pi integral minus infinity to infinity x of j omega e raised to j omega t with respect to d omega. So we can find x of t from x of j omega by using inverse Fourier transform. So using this we can try to prove this. Firstly, this is the x of t, then d by dt of x of t will be d by dt of this integral. We can take the differential in both sides. So again, if you are looking here, this integral is with respect to d omega, only time function is e raised to j omega t. So we can take inside this d by dt. Differential will depend only to this or affect only to this function e raised to j omega t. So again, d by dt of e raised to j omega t is e raised to j omega t into j omega. So it become like this, e raised to j omega, differential is e raised to j omega t into j omega. Then we can say this, we can write as it like j omega into x of j omega. We can combine this j omega and x of j omega, so it become j omega x of j omega. So if you are comparing this and this, so if this is like x of j omega is the Fourier transform of x of t. Similarly, if you are looking here, the Fourier transform of d by dt of x of t is j omega x of j omega. So we can write as Fourier transform of this d by dt of x of t is j omega x of j omega, hence the proof. And in general we can say that this is only one order differentiation. So if you are differentiating n times d raised to n by dt raised to n x of t, you can extend this result as j omega whole raised to n x of j omega. Next property is differentiation in frequency. Now in previous we discussed the differentiation time, d by dt of x of t. Here it is d by d omega of x of j omega, j omega. So here it is differentiation frequency domain. So the property states that it is Fourier transform of t x of t is equal to j d by d omega of x of j omega. So we can start from we have the equation for Fourier transform as x of j omega equal to f of x of t is equal to integral minus infinity to infinity x of t raised to minus j omega t dt. So we can write this. So this we will get like this. So we can differentiate this. So we will get d by d omega x of j omega equal to d by d omega of whole this integral. Again, this is with respect to d omega, and this is time function and this dt also. So only omega function is e raised to j omega t. So we can take inside this integral differentiation into like this, d by d omega. It will affect only e raised to minus j omega t. Again, d by d omega of e raised to minus j omega t is e raised to minus j omega t into minus jt. It is with respect to d omega. So t is constant, omega is the variable. So e raised to minus j omega t into minus jt, and we can take this minus j outside. So it become minus j integral t, and this t and x of t can be written together. So t x of t e raised to minus j omega t dt. So again minus j is 1 by j. Okay, minus j is equivalent to 1 by j. If you are multiplying by j numerator and denominator, it will become j square. So it become minus 1 denominator j. So minus j is equal to 1 by j. So we'll get like this, and we can take this j into this side. So it become j d by d omega x of j omega equal to integral minus infinity to infinity t x of t e raised to minus j omega t dt. Then we can compare this. So here the Fourier transform of x of t is x of j omega. So comparing this, Fourier transform of Tx of t is equal to this one. So we can write as Fourier transform of Tx of t is equal to j into d by d omega of x of j omega. Then the property is proved. Next is duality. So this property states that Fourier transform of x of t is x of j omega, then f of x of t, capital X of t is equal to 2 pi small x of minus omega. Here what is we have done is, this is x of t, this is x of minus omega, this is x of j omega, this is x of t. We are interchanging the domains. Okay. So again we are starting from, we have the inverse Fourier transform formula as x of t is equal to 1 by 2 pi integral minus infinity to infinity x of j omega e raised to j omega t d omega. Then we can write this, then x of minus t, we can take x of minus t, so t become minus t, so here this t become minus t, so e raised to minus j omega t. So again we can take 2 pi this side, so it become 2 pi x of minus t, and this integral x of j omega e raised to minus j omega t d omega. Then we can interchange t and omega, so this become this t become minus omega, minus t become minus omega, this j omega become t, then this become e raised to minus j omega itself, omega and d, and this d omega become dt. So we can say that, so comparing, we have Fourier transform equation f of x of t is equal to x of t raised to minus j omega dt. Means this is actually the Fourier transform of x of t. Then comparing this x of t, Fourier transform of this one will be 2 pi x of minus omega. Hence the proof. Next one is convolution property. So if there are two signals x1 of t and x2 of t, and their Fourier transforms are x1 of j omega and x2 of j omega, then the Fourier transform of their convolution x1 of t star x2 of t is equal to product of their Fourier transforms x1 of j omega into x2 of j omega. So we have the Fourier transform equation as this. So for finding the Fourier transform of this one, we have to replace x of t by x1 of t star x2 of t. Then we can substitute the equation. We know the convolution is integral minus infinity to infinity x1 of tau x2 of t minus tau d tau. This is the general equation for finding convolution. So we can rewrite it as by substituting the integral formula, and we can now interchange the order of integration. Means now this is first one is d tau with respect to d tau, and the second we are doing with respect to dt. So first we can do with respect to dt. So dt terms are x2 t minus tau and e raised to minus j omega t dt, and at that time x1 of tau is constant, so we can take x1 of tau outside, and with respect, and finally with respect to d tau. So now we can write like this, x2 of t minus tau e raised to minus j omega t dt. And if you are looking here, this is actually we have the Fourier transform of x of t as x of j omega. So this is similar. So we can write that as, this is actually Fourier transform of x2 of t minus tau. It's actually x of Fourier transform of x of t. So this is similar. The only difference is here x of t, here it is x2 of t minus tau. So this is actually the Fourier transform of x2 of t minus tau. And again we have the shifting time shifting property discussed in previous lecture. This will be equal to if x2 of j omega is the Fourier transform of x2 of t, we can write the Fourier transform of x2 of t minus tau as e raised to minus j omega tau x2 of j omega by using shifting theorem. So again x2 of j omega is a constant, so we can take it outside, so it become x2 of j omega integral minus infinity to infinity x1 of tau e raised to minus j omega tau d tau. So comparing these two, the only difference is here is x of tau t, here it is x1 of tau. So this is actually Fourier transform of x of j omega, so this will be Fourier transform of x1 of j omega. So it become x2 of j omega into x1 of j omega, means product of individual Fourier transforms. So we can say that Fourier transform of x1 of t convolution x2 of t is equal to x1 of j omega into x2 of j omega. Hence the proof. So with this we can wind up the session. Thank you.